write it down. So why, this is a remark again. So the remark is, why would we actually be interested in chains, cycles, or boundaries? So recall, we want to find holes. We want to classify our topological spaces. I'm denoting it with TS, and one of the way is to find holes inside it. Okay, so this was the motivation, and now we developed some tools, mathematical tools. So now we want to find things. I'll explain what these things are in a bit. So we want to find things that do not have boundaries, but they themselves are not boundaries of anything. So the thing that I said that, oh, we want to find holes, right? So if I take this sentence and formulate it in a logical order with the mathematical terms, a little bit, that is what I would like to say. This would translate into this. So we want to find out things that themselves have no boundary, but at the same time they are not boundaries of anything else. Okay, that's what our goal is from the very beginning. And to find those things, we developed all these simplexes, chains, boundaries, boundary operator. That's why we did all those things to come to this point. So now if I translate into this thing into mathematics that we developed so far, this would mean that we are interested in chains that are elements of the cycles Z and K, but they don't belong to the boundary set. So this is what it means. That means we want some chains. That's what these things are. We want chains that are not boundaries, and at the same time they don't have a boundary for themselves. So it's not a boundary at all, and at the same time it doesn't have a boundary too. That's what we are interested in. Okay, and this is well formulated into idea of the finding homology groups. So this is where the idea of the homology groups come in. And the basic idea to find such chains is to just compute the group given by Z and K quotient with BK. And what this intuitively means is that you take all the elements of Z and of K, that means all the elements of the cycles, and you take all the elements of the boundaries. And you know that all the elements of the boundaries will also be inside all the elements of cycles, right? Any element that belongs to the boundary will also belong to the cycle as well. And then what you do is that you distinguish this element. So let me draw a visual diagram for you. So let's say this is your Zn of k, okay? Let's say this is some Zn of k, boxes, 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 box, and another box, like this, 5 boxes, let's say. And the ones marked with this red color, these boxes, they also belong to the boundary group, or the boundary, the set of all n boundaries, okay? So what you do, you take these 2 elements and you shrink them to the identity. Let's say this is how the identity looks. Again, this is a purely visual diagram. You already know that every group will contain an identity, and the identity elements in a group are unique. So when you shrink them to identity, you are essentially getting rid of everything that is not a cycle, right? So all these elements you have right now are the things of interest. These green guys, so they are the things of interest. And once you compute this, once you take these boundary elements to identity, you just write it as modulo b of n of k. Okay, so that's why it's written like this, and sometimes people call it, the thing that we are computing by this notation, with this notation, it's actually the Zn factored by the group Bn. And this is what the homology group is. In fact, this is how it is defined. The nth homology group is given by this, and we'll talk more about these homology groups after this. So this is just now, take this as an algebraic definition. The nth homology group is this, and we are interested in computing different h of n's of k. That means if we have a simplicial complex k, we want to compute different homology groups for k. That's what our ultimate goal is, and that will help us to find these holes.